Hi everyone, this is my report for Lab 1. I chose the rolling of a tennis ball for the case of a constant velocity motion. First of all, let me talk about the principle involved. We know that according to Newton's second law, or equivalently by the momentum principle, Vf equals Vi plus F net by m times delta t, or by momentum principle, m times Vf equals m times Vi plus F net times change in time, or delta t. Now in this, if we set net force or F net equal to 0, Vf equals Vi, that is the initial velocity is the final velocity, and hence this is the case of constant velocity motion. The position of the ball can be given by Rf, which is the final position, equal to the initial position plus initial velocity times change in time. This is the tracker video I have recorded. Since we have to consider the constant velocity case, I've considered only that part of the video where the ball gains a constant velocity. To show this, I have marked center of mass for two videos to create two models. This is the positive x direction. This is the origin, which is the starting frame. The ball diameter 0.07 meters. Now if I play the video, the points of masses are shown. You can see that the graph is a straight line which shows linearity and hence is a constant velocity case. Now the other video I have recorded is the same video, but I have reduced the time for it. I'll explain this in a moment, why I have done this. This is the other video. For the first video, the start time is 0 second, where the ball is at 0.022 meters and has initial velocity equal to 0.524 meters per second in the negative x direction, and the time of last observation is 0.917 seconds. For the second video, the start time is 0 second, the ball is at 0.022 meters and the initial velocity is 0.524 meters per second in the negative x direction. The time of last observation is 0.542 seconds. Now let me show you the Python codes for the two models. This one is the Python code for the first model, which says that the mass of the ball is 0.056 kgs. I have set the initial position of the ball at the origin, which is 0, 0, 0, and the ball velocity is minus 0.524, which shows that the velocity is in the negative x direction. Delta t has been set to 0.01 and time has to be less than 0.917 seconds for the first model case. This statement applies the Newton's second law. Right, let me just play this for you. Yeah, as you can see, the ball moves towards the left and the graph is a straight line. Let me just show you again the tracker video for the first model, which is this one. You can see that the ball moves in the left or the negative x direction. Now let me show you the second model Python code, which is again almost the same, with only change that the final time is 0.542 seconds. As you can see, it is almost the same reduced version of the first model. Let me show you the spreadsheet for the two cases. This is the spreadsheet for the first video. If you observe the endpoints of this spreadsheet, the difference between the y-axis coordinates is about 0.08 meters. This is minus 0.48 and this is minus 0.40, so the distance is approximately 0.08 meters. For the second model, the difference between the y coordinates of the endpoints is 0.04 meters, minus 0.28 and minus 0.24, so the difference is 0.04 meters. Hence you can see that the difference decreases as I decrease the time. Let me first tell you the possible reason for the difference in model and the observations. The first one could be that we assume that the net force acting on the ball is 0, but it is not true actually. There could be a small amount of force acting on the ball. Also, a tennis ball has a very small mass, therefore effect of even a small force on the ball's velocity is greater. This can be seen from Newton's second law as follows: dF equals Vi plus Fnet by m times del t. Now let Fnet approach 0. A heavier ball will make Fnet by m even smaller and therefore will be more closer to 0. Hence, as seen in the spreadsheet graph of the two models, observed position suggests that the velocity is decreasing. This shows that some opposing force is acting. Hence, I made two models to rectify the problem. In the first one, I considered the decreasing velocity of the ball as well. Therefore, more amount of deviation is observed for it in the spreadsheet, since the model considers a constant velocity, whereas in the experiment the velocity is decreasing. As I limit the time, I consider only the constant velocity part of the ball motion, and hence the deviation decreases in the second model. If we flip the orientation of the axis, the ball would move in the positive x direction instead of negative x direction, and the velocity vector would be directed towards the positive x direction. It is not possible to say how many forces add up to give zero net force, since the net force is not zero. But if we assume net force to be equal to 0, these would be the components adding to give net force.